We've been talking about music and pitch and frequency and sound waves and all kinds of fun stuff. And what I want to do is I want to go ahead and I want to actually extend this into musical instruments a little bit. How do musical instruments make sound? How do they make notes? How does a small vibration from you end up being an actual loud note being played on an instrument? Okay? And the answer to this is resonance. Okay? Now, we didn't spend a heck of a lot of time talking about resonance, but the easiest example of resonance is if you've ever pushed a little kid on a swing. Okay, they're hanging down here on their swing, and you give them a little push. Okay, and they move back and forth. And then you give them another little push, and they go a little bit higher. And then you give them another little push, and they go a little bit higher. Okay, and the idea is you can add just a little bit of energy at a time, and it gives you a really, really big swing. Of course, that's only true if you're pushing at the right time. If you're pushing right here, while they're coming this way, you're going to slow them down and stop them. Okay, so resonance is this reinforcement of the vibration that's happening at a natural frequency. Okay, so this reinforces a vibration. Now, which vibration, what's the natural frequency, which vibration is it actually going to reinforce? Well, to answer that question, we need to go back a little bit to standing waves. Okay, remember, an object can hold a standing wave depending on the string, right? We looked at this in strings. Okay, if we have a string that's fixed on both ends, okay, that means both ends are nodes. They're forced to be right in the middle of the wave. They don't vibrate up, they don't vibrate down. But if you can generate a wave that fits exactly between two nodes, okay, then you get this standing wave. Okay, and the antinodes vibrate back and forth. That's this part, right? Antinode, maximum displacement. And the nodes don't appear to move. And you can have half a wave, or you can have a full wave, right? And then its reflected wave comes back, flips over on the other side, looks like that. Or you can have 1.5 waves, okay? Or you guys remember these, right? So you can get nodes and antinodes and all kinds of fun things. Well, these vibrations reinforce each other, and that's why this node, it's dead here, it's vibrating just a little bit, but you get big waves in the middle. It's resonance, okay? Well, instruments do the same thing. And what we want to look at is we want to look at air columns, okay? Because a lot of the instruments we play, like a trumpet or a saxophone, clarinet, a flute, these all rely not on the vibrations of strings, but on the vibration of an air column. In fact, if you think about a trumpet, okay, you've got a mouthpiece on one side, and then it's a big long brass tube, and it spirals around a little bit, and I can't draw, and then there's the bell on the other side, and sound comes out of that, right? And you've got valves that you can control. Anyways, how does this work? Well, you put in a small vibration here. Your lips actually, as you blow air through them, they vibrate, and that causes the air in here to vibrate. Okay, and to get a note, a nice sound coming out of this, you've got to blow just right so that the vibrations that you're creating are reinforcing a standing wave in the trumpet. Well, what kind of wave can the trumpet hold? Okay, well, to think about this, we're going to simplify it with just an open tube. Okay, an open tube, I mean like a pipe. Both ends of this are open. Okay, they're open to the air. So you can put in a vibration here, and these ends both act as boundaries. Okay, now this open end is also a boundary. If you think about it, the air in this tube is contained, the air in the room is not, and so this is actually a boundary. Something different is happening there. Okay, well, we need to think about what's actually going on, because a sound wave is a pressure wave. Okay, now zero sound means that there's no difference in pressure between the inside of this thing and the outside of this thing, right? So there's the pressure in the room, there's atmospheric pressure, and that's our median. That's our zero pressure, that's our no wave, that's our rest position. Okay? So our rest position, if you like, is atmospheric pressure. It's the background pressure. The sound comes when we increase or decrease that pressure, right? We create a vibration, so all these little air molecules are nice and evenly spaced. We create a vibration, we push a few of these together, and that spreads a few more of them out. Okay, now we've changed the pressure in the room. Anyways, okay, we want to look at this pipe and we want to figure out what's happening on the ends. Well, if you think about this, since both ends are open to the room, okay, this can't be high pressure or low pressure, because as soon as the pressure changes from the room pressure, the air is going to flow one way or the other to equalize that pressure. So this is a forced rest position. So this is a node, okay, as is this. This is also a node. So when you have an instrument that's open on both sides, okay, open on both sides, you have an instrument that's like a stringed instrument. It's got a node on both ends. And if we go back to that little drawing, okay, if it's got a node on both ends, we know what size waves can fit on it. Okay, we can have a wave that is twice the length of the instrument. We can have a wave that is the length of the instrument. Okay, and so what we're talking about now is these things called harmonics. Okay, an instrument has a fundamental frequency or a fundamental wavelength. Okay, and fundamental is the longest wave that'll fit. Okay, the fundamental frequency is the longest wave that will fit, and when we have an instrument that has the fundamental frequency, we're also going to have other waves that'll fit on there. Okay, so fundamental wavelength or fundamental frequency, this is the longest wave, which is going to correspond to the lowest frequency that'll fit or a musical instrument can play. Okay, and for a tube that's open on both ends, the fundamental frequency or wavelength 1 is equal to twice the length of the instrument. This is for open. Now, this is called the first harmonic, okay, or the fundamental frequency, and we can look at this and we can say, okay, well, what's going to happen to this? What other lengths fit? Well, since these are all going to be multiples of half wavelengths, right? So the next wavelength that fits, okay, is going to be an entire wave. It's going to fit all the way on there. And the next one that fits, the third wavelength, is equal to 1.5 waves, okay, but you've got to think about how this fraction is working. This is 2 over 1. This is 2 over 2. This will be 2 over 3 times the length, okay? Which means if you think about this, lambda 1 is 2L, lambda 2 is 2 over 2L, lambda 3 is 2 over 3L. So the nth wavelength that'll fit in an open column of air is given by 2 over n times L. Okay, so that's the length of a wave that'll fit, and n is actually the harmonic that we talk about. Okay, so n here can be 1, 2, 3, 4. So this can produce the first harmonic, the second harmonic, the third harmonic, the fourth harmonic. Okay, these are the different wavelengths that'll fit. Okay, now if you think about how frequency and wavelength are related, V is equal to wavelength times frequency. Okay, that is a funny looking lambda. Anyway, since velocity is wavelength times frequency, what we have is this inverse relationship between wavelength and frequency. Okay, and so you can see here that my wavelength keeps getting shorter. It gets shorter by half. It goes from 2 to 1. Okay, and then it gets shorter and shorter and shorter. Right. So n is going. This will be 2 over 1, then 2 over 2, then 2 over 3, then 2 over 4, then 2 over 5, then 2 over 6. Okay, so what's actually happening to the frequency? The frequency is getting higher, right? And so the fundamental frequency of the first harmonic is going to be the lowest note we can get, and then we can get higher notes from there. Okay, so let's go to a different type of tube. Okay, now not all instruments are considered open on both ends. Like a reeded instrument is generally considered closed on the reed side. Okay, yeah, that's where you put in a vibration, but the air really can't move back the other way there. Okay, it's a closed open tube. Now, I want you to think about what that means. Okay? If it's a closed on one side, that means that this is not going to be able to equalize the air pressure around it. That air is isolated, okay? Which means this end is going to keep changing between high pressure when a wave comes in and low pressure when the wave comes out. It's an antinode. Okay? It's an antinode. It's not forced to be at the rest position. It can't be at the rest position. It's going to keep switching back and forth between high and low pressure, whereas this open end is still a node. Okay, now that is a little bit different, because if we go back to the wave on a string example, okay, if I'm saying that this end is fixed as either a high or a low, that means the wave is going to be up here or down here. Okay, and so what wavelengths will fit now, but this end still has to be a node? Well, if you think, I could put that end right here. It's a node. Well, how much of a wave is that? From a crest to a node, that's a quarter of a wave. Okay, that means the shortest, or not the shortest, the longest wave that'll fit in this tube right here, if this is tube of length L, the wavelength is equal to 4L. Okay, the wavelength is equal to 4L. That's our fundamental wavelength. It can be 4 times longer than the tube, which means when you have an open closed instrument like this, okay, you can get a pretty low frequency, a low pitch note, even if the tube is fairly short, because it'll fit a quarter of a wave on it. Okay, now will it fit a half of a wave on it? Okay, well, the answer to that is no. A half of a wave would be antinode, antinode, and we can't do that. Okay, now what we do here is we look at this and we say, well, that would be the next thing in our pattern, quarter, half, but that doesn't fit. So we don't have a second wavelength. Okay, this is non-existent. Okay, do we have a third one? Okay, well, sure we do, because now we're back to another node, another quarter over here. Okay, and so what we're going to have on this one is that we can produce waves with length 4 over n, okay, but this time n is restricted to an odd number, 1, 3, 5. Okay, so we can have 4, we can have 4/3, we can have 4/5, we can have 4/7, but we cannot have an entire wave fit on the curve. We can only have quarter and then half intervals from there. So if you'd like, you can think of it as quarter plus half, and then we can add another half of a wave plus half, then we can add another half of a wave. Okay, but we can't add another quarter in there. We skip that one. Okay, which is why we count by odds down here. So an open closed resonator only produces the odd harmonics, or the odd odd wavelength notes. Okay, now it turns out they can produce multiple notes at the same time, but you can use these things to kind of help you think about the notes that a musical instrument produces. Based on the shape of an instrument, you can kind of predict what it's going to sound like, because you can figure out what size waves will fit in there. And remember, a longer wave means a lower frequency, and a shorter wave means a higher frequency. Okay. Now, there's going to be a couple problems I want you guys to try to take a look at that deal with the open or closed tubes, or even maybe a string. Okay, but what I want you to do is I want you to take a look at page 416, and I want you to look at numbers 18 through 21. Okay, and this is going to deal with the resonance in a length of air. Okay, and then also I want you to take a look at, I just want you to read through a little bit on fundamentals and harmonics, which is just a short little blurb in your book on page 417. Okay, so read page 417. Alright, now I am going to do one of these example problems for you. I'm going to do number 20 on page 416. It says the frequency of a tuning fork is unknown. Okay, F unknown. Okay. A student uses an air column at 27 degrees Celsius. Okay, so the temperature of air equals 27 degrees Celsius, and finds resonance spaced 20.2 centimeters. What is the frequency of the tuning fork? Use a speed calculated in example problem 2 for the speed of sound in air at 27 degrees. Okay, says he finds resonances spaced at 20.2 centimeters. Now we have to stop and think about what that means. Okay, well, if we're getting these at intervals of 20.2 and it's not skipping, right? If it'll go 20.2 and then 40.4 and then 60.6, we know that this must be an open tube, okay? Which means if 20.2 centimeters is our first resonance, okay, then we can actually go through and we can say, well, that must mean that's half a wavelength, because every half wavelength we get this. So an entire wavelength for this wave is 40.4 centimeters. And we know from the example problem that the velocity of the wave is 347 meters per second in air at 27 degrees. Okay, and so we're just supposed to find the frequency of this thing. Well, V equals wavelength times frequency, and so 347 equals 0.404, right? You got to change that to meters, times F. So if we take 347 divided by 0.404, we see that we get a resonance frequency of 859, essentially, hertz. Okay, so F equals 859 hertz. So you got to go through and think about how the standing wave is fitting and what wavelengths are fitting in the column. Okay, so work through those 4 or 5 problems there, and hopefully they make sense. We'll talk a little bit more about this tomorrow.